Hi, and welcome to this presentation of the high-performance servo drive solution provided by Analog Devices. Let's start by having a quick look at the agenda. First, we'll discuss about the design and the various hardware components that make up the Analog Devices high-performance servo drive solution, and we'll see what reference designs are provided by ADI together with the hardware and what is the support model for the complete package. Next, we'll take a look at the features of the intelligent drives kit provided by Analog Devices in conjunction with Avnet, Xilinx, and Networks. In the end, we'll see what are the purchasing options for the kit, where it can be purchased from, and where to find more information about the Analog Devices hardware, reference designs, and about the workflows of using the high-performance servo drive solution with Networks and the Xilinx Zinc 7000 all programmable SoCs. Let's have a closer look at the hardware. The Analog Devices high-performance servo drive is a complete motor drive system demonstrating efficient control of multiple motor types. It consists of two boards, a controller board and a drive board. The system incorporates high-quality power sources, reliable power, control, and feedback signals isolation, accurate measurement of motor current and voltage signals, high-speed interfaces for control signals to allow fast control response, industrial Ethernet high-speed interfaces, flexible control with FPGA or SoC interface. Example reference designs showing how to use the control solution with Xilinx FPGAs or SoCs and Simulink from Networks are provided together with the hardware. Target applications of the system include industrial servos and drives, manufacturing, assembly and automation, medical diagnostic, surgical assist robotics, video surveillance and machine vision, and power-efficient drives for transportation. The controller board is a mixed-signal FPGA mezzanine card, or FMC, designed to connect to any Xilinx FPGA or SoC platforms with low pin count or high pin count FMC connectors. It features current and voltage measurement using isolated ADCs, an isolated Xilinx XADC interface, fully isolated digital control and feedback signals, whole differential whole encoder and resolver interfaces, 2 gigabit Ethernet PHYs for high-speed industrial communication, FMC signals voltage adaptation interface for seamless operation on all FMC voltage levels. Full isolation of the analog and digital signals ensures that the FPGA platform is always protected from the dangerous voltages that can arise on the motor drive side. Let's take a closer look at the various components present on the controller board. The connection to the Xilinx FPGA SoC platform is done through a FMC low pin count connector. A set of LEDs are used to signal the state of the different power supplies needed by the board. The ADG3308 8-channel bidirectional lever translator adapts the 1.25, 2.5, or 3.3 digital signal levels that can be found on the FMC connector to the 3.3 digital signal level of the board. The ADUM7640 triple-channel digital isolator provides isolation for all digital I/O signals on the FMC interface. The ADUM 5000 integrated isolated DC to DC converter provides isolated power to all the digital and analog isolation chips. The AD7401A isolated second-order sigma delta modulator digitizes the analog current and DC bus voltage feedback signals. Current measurement is performed for two phases of the motor and for the total current. Motor position and speed sensing can be done using either single-ended or differential Hall sensors, encoders, back EMF, or a resolver. The hardware conditions the sensors signals and sends clean digital signals to the FPGA. Sensor selection is done with jumpers that control the selection lines of the ADG704 4-channel multiplexer. The AD2S1210 variable resolution 10-bit to 16-bit resolver to digital converter interprets the signals generated by a resolver and outputs digital position and speed data either on a SPI interface or as encoder-like signals. The Marvell 88E1512 integrated gigabit energy-efficient Ethernet transceiver connects to the FPGA through the RGMII interface. Either the hardmax of the Zinc or the Xilinx Ethernet IPs can be used to interface with the PHY. This high-speed Ethernet interface allows the implementation of industrial communication protocols like Profinet, EtherCAT, or PowerLink. The connection to the drive board is done through a high-performance mixed-signal connector with a low distortion and excellent shielding capabilities for both the analog and the digital signals. The drive board contains all the power electronics needed to drive the motors as well as current and voltage sensing and protection circuits. It can drive brushless DC, PMSM, brushed DC, and stepper motors up to 48 volts at 18 amps. It has dynamic braking capability and integrated overcurrent and reverse voltage protection. Current measurement is done using isolated ADCs. Programmable gain amplifiers are used to maximize the current measurement input range. It provides to the control board DC bus voltage, phase currents, and total current analog feedback signals. The board has integrated back EMF zero-cross detection for sensorless control of PMSM or brushless DC motors. Let's take a closer look at the components present on the drive board. Current sensing is done using shunt resistors. The AD7401A isolated second-order sigma-delta modulators digitize the current feedback signals. Current measurement is performed for two phases of the motor and for the total current. The AD8207 high-voltage, zero-drift bidirectional difference amplifier, the AD8630 single-supply, zero-drift, rail-to-rail quad operational amplifier, and the AD8251 programmable gain amplifier are used to condition the analog, current, and voltage feedback signals that are sent to the control board. The IRS-2336D high-voltage, three-phase integrated gate driver IC from IRF drives the MOSFET bridge. The gate driver takes as input three pairs of complementary PWM signals with a frequency up to 150 kHz and has integrated dead-time protection. An enable signal is used to stop the driver. The integrated overcurrent detection circuit stops the driver when an overcurrent condition occurs and provides a feedback fault signal. The ADUM5230 isolated half-bridge driver with integrated high-side supply is used to drive the MOSFET that shuts down the power to the entire board when an overcurrent condition is detected to avoid board damage. The CMP04 quad precision comparators are used to implement the back EMF zero-crossing detection circuitry for sensorless motor control. The ADP1621 constant frequency current mode step-up DC to DC controller provides power to the entire board. The ADP2301 step-down regulator provides the 5 volts power needed by some of the components on the board. The ADP7102 CMOS LDO is used as a 7 volts power source, while the ADM660 CMOS switched capacitor voltage converter is used as a -7 volts power source. The most important part in the current and voltage feedback signal chain is the AD7401A second-order isolated sigma-delta modulator. This high-performance ADC has a resolution of 16 bits, no missing codes, an effective number of bits of 13.3, and a SNR of 83 dB. The plus-minus 250 mV differential analog input range and the high common mode voltage allows it to measure directly the small voltages across the shunt resistors. It is ideal for applications like motor control, DC to AC inverters, shunt resistor current feedback sensing, and isolated voltage measurement. The AD7401A has two digital signal wires, a clock input of up to 20 MHz and a 1-bit digital data stream output. The actual ADC codes are reconstructed using a Sync3 digital filter. A filter model and HDL implementation are provided in the datasheet, giving an output code of 16 bits and a sampling rate of 78 kHz. The output code resolution and sampling rate can be controlled by changing the filter's model and decimation. While the 78 kHz sampling rate might be good enough for many applications, there are situations when higher sampling rates are required. In these cases, polyphase interpolation filters can be used to increase the sampling rate of the system up to 10 megasamples per second of true 16-bit data. The measurement path for currents and voltage are divided between the controller and the drive board. Let's have a closer look at how the measurement of these signals is done. We'll start with the currents for the A and B phases of the motor. The currents for the A and B phases are sensed using 6 milliohms shunt resistors. There are two possible measurement paths showing measurement techniques for the case when the ADC can be placed close to the shunt resistor and for the case when the ADC cannot be placed in the proximity of the shunt resistor. Both techniques aim to get the best measurement accuracy. When the ADC is placed in the proximity of the shunt resistor, the signal path between the shunt resistor and the ADC is very short and less prone to noise coupling. The small differential voltage on the shunt resistor is measured directly with the AD7401A isolated sigma delta modulator without the need of extra interfacing and signal conditioning circuitry. The digital data and clock signals of the ADC travel the entire length of the drive and controller boards all the way to the FPGA. Since the analog signals were digitized close to the source and sent in a digital format to the FPGA, there are no concerns related to the quality of the measurements. When the ADC is not placed in the proximity of the shunt resistor, the signal path between the shunt resistor and the ADC is long and very prone to noise coupling, especially due to the switching noise of the power stage that's driving the motor and to the motor itself. Special care must be taken in properly designing the signal conditioning circuitry that sits between the ADC and the shunt resistor and in properly shielding the analog signals on the way to the ADC. The small differential voltage on the shunt resistor is amplified on the drive board with the AD8207 difference amplifier placed close to the shunt resistor in order to avoid noise coupling. The signal is amplified from the plus-minus 125 mV input range to a plus-minus 2.5 volts range to minimize the effect of the coupled noise. The amplified signal goes on the drive board through another programmable amplification stage done using the AD8251 PGA. This ensures that the ADC will always receive at input signals properly scaled to fit its input range. The amplified analog signals go through the connector to the controller board. The connector has proper shielding for each analog signal to mitigate noise coupling. On the controller board, the analog signals coming from the drive board are transferred from the plus-minus 2.5 volts input range to a plus-minus 250 mV range suited for the AD7401A sigma delta modulator. The attenuation is done using the ADA4084-2 amplifier. The IA and IB XADC measurement chain utilizes the entire path of the regular measurement chain and adds on the controller board after the AD7401A a Salem key analog reconstruction filter implemented using AD8646 operational amplifiers. The combination between the isolated sigma delta modulator and the analog reconstruction filter provides a convenient and cheap way to achieve analog isolation of the XADC input signals without compromising the quality of the measurement. The signal path for the total current measurement is almost identical to the one for the A and B phases. The differences arise because of the range of the total current compared to the A and B phase currents and are reflected just in the value of the shunt resistor and of some gains along the signal path to the ADC. DC bus voltage sensing is done on the drive board using a resistive divider and an attenuation circuit implemented with the AD8207 operational amplifier. The analog signals go through the connector to the control board. On the control board, the analog signals coming from the drive board are transferred from the 0 to 5 volts input range to a 0 to 250 millivolts range suited for the sigma delta modulator. The attenuation is done using the ADA4084-2 amplifier. As in the case of the phase and total currents, the DC bus voltage XADC measurement chain utilizes the entire path of the regular measurement chain and adds on the control board after the sigma delta modulator a cell key analog reconstruction filter to achieve analog isolation of the XADC input signals. The analog device's dynamometer is a dynamically adjustable load that can be used to test real-time motor control performance. It consists of two brushless DC motors directly coupled through a rigid connection. One of the brushless DC motors acts as a load and is controlled by the dyno's embedded control system, while the second motor is driven by the ADI high-performance servo drive. The load is controlled by changing the PWM field factor of the three-phase MOSFET bridge which connects the load motor's leads in a delta topology. The system is equipped with an LCD which displays information about the current generated by the load and its speed. Together with the three push buttons, it can be used to display and configure different system parameters. The plus-minus buttons are used to navigate through the system's menu and to change different parameters such as load profiles and load magnitude, while the Enter button is used to confirm parameter changes or to enter/exit the menu screen. External control can be achieved by using the Analog Discovery USB oscilloscope for low signal capture and control directly from MATLAB using the Instrumentation Control toolbox. Let's have a look at the reference designs that ADI provides together with the high-performance servo drive hardware. Together with the hardware platform, Analog Devices provides a set of reference designs intended to give a starting point for anyone who wants to evaluate the system and help kickstart any new project based on the ADI high-performance servo drive. All the reference designs are open source. On the HDR side, two types of reference designs are provided. An ISC HDR project with a chipscope interface that allows system control and monitoring of all the digital and analog feedback signals like motor speed, currents, and DC bus voltage. The speed of a brushless DC motor can be controlled in manual mode using a 6-step driving scheme by specifying the field factor of the PWM signal. The purpose is to provide a simple to understand and utilize project that can be used to rapidly evaluate the system. The Vivado HDR project has complex blocks with XI Lite and XI streaming interfaces. It includes automatic controllers implemented in HDR from Simulink models using the Metworks tools for automatic HDR code generation. This project provides a complete infrastructure for Linux support. On the software side, a complete Ubuntu Linux system is provided. This includes the Linux I/O drivers needed to interface with the Analog Devices high-performance servo drive, a user space application for monitoring and control called I/O Scope, and an I/O server that allows real-time data acquisition and system control over TCP or UDP together with I/O clients running on a remote computer. The reference designs include also the Simulink models of the provided controllers. This high-level diagram shows how the ADI reference design is partitioned on a Xilinx Zinc SoC. The programmable logic implements the IP cores for interfacing with the ADCs, position sensors, and the motor drive stage. The field-oriented control algorithm provided by Metworks is integrated into an Analog Devices IP. All the IPs have low-speed XI Lite interfaces for configuration and control, as well as high-speed XI streaming interfaces that allow them to transfer to the software level real-time data through EMA channels. The high-speed Ethernet interface can be implemented either using the hard MACs on the Zinc or the Xilinx Ethernet IPs in the programmable logic. The ARM Cortex-A9 processing system runs Ubuntu Linux and the I/O-Scope user space application, both provided by analog devices. An HDMI output is used to display the Linux interface on a monitor, while a keyboard and mouse can be connected to the system on a USB 2.0 port. The Linux Industrial I/O subsystem is intended to provide support for devices that, in some sense, are sampling data converters such as ADCs and DECs like the AD7401A, gyros and IMUs, capacitors to digital converters, pressure, temperature and light sensors, RF transceivers like the AD9361. The I/O subsystem is included in all mainline Linux kernels and is now used by all the Linux drivers that ADI provides for its parts. The I/O-Scope is an open-source Linux application developed by Analog Devices. It runs on the dual ARM Cortex-A9s inside the Xilinx Zinc and has the ability to display real-time data acquired from any Analog Devices FMC card connected to the Xilinx Zinc platform. The data can be displayed either in the time domain, frequency domain, or as a constellation plot. Different popular file formats like comma separated values or .mat MATLAB files are supported to save the captured data for further analysis. The I/O-Scope provides a graphical user interface for changing or reading back the configuration of the Analog Devices FMC cards. The I/O server allows real-time data acquisition and system control over TCP or UDP together with I/O clients running on a remote computer. The server runs on an embedded target under Linux and manages real-time data exchange over TCP or UDP between the target and a remote client. Data exchange is based on a simple communication protocol. There are a few flavors of I/O clients. The C and C# I/O clients can be used as plugins in any desktop application, while the MATLAB I/O client is designed to be integrated in native MATLAB applications. The MATLAB I/O client is based on the UDP receiver and UDP sender classes from the MATWORKS DSP toolbox. It can control the embedded target using specific commands and acquire real-time data from the embedded target. Let's see now what is the support model for the ADI high-performance servo drive. The ADI high-performance servo drive is supported through the main ADI website, which is analog.com, the ADI Wiki, wiki.analog.com, the ADI Engineer Zone, ez.analog.com. On analog.com, you can find for any ADI part, datasheets and documentation, design tools and models, evaluation kits, and also information on how to get samples and buy the part. On the ADI Wiki, you can find comprehensive documentation about the servo drive, including schematics, Gerbers, bill of materials. From the Wiki, you can also download the reference designs, including HDL, applications, and drivers for Linux and OS, and Simulink control models. The Engineer Zone is an online support forum where you can get answers for any questions you might have about the system. It is divided into communities specialized on different areas. For the high-performance servo drive system, the communities of interest would be data converters, interface and isolation, power management, FPGA reference designs, and the Linux and microcontroller device drivers community. To find the high-performance servo drive documentation on the wiki, go to this link or search for motor control on wiki.analog.com. The wiki is structured as a user guide where you can find information about how to set up the system, both from a hardware and software perspective, a complete description of the different hardware components, including block diagrams, schematics, layout file, Gerbers, and bill of materials, documentation and source code for the HDL designs, documentation and source code for the Linux drivers and applications, Simulink controller models, and links to get further help and support. This is how the engineer zone, ez.analog.com, looks like. It is divided into communities specialized in different areas. For the high-performance server drive system, the communities of interest will be data converters, interface and isolation, power management, FPGA reference designs, and the Linux microcontroller device drivers communities. These are all very active communities where you can get answers to questions from the engineers that have actually worked on the parts or systems that you are interested in. The Intelligent Drives Kit is the result of the combined efforts of Analog Devices, Avnet, Xilinx, and Networks to provide a complete motor control prototyping system that can help accelerate the process of moving your system from concept to production. The kit includes the Avnet Z board, a Xilinx Vivado Design Edition voucher, the Analog Devices FMC Modcon 1 module, an 8 GB SD card programmed with the ADI Ubuntu Linux image, including drivers and application software, HDL and software source code, reference designs, full schematics and Gerbers, a 24 volts 4000 RPM brushless DC motor with Hall sensors and a 1250 CPR indexed encoder, the optional Networks motor control design package, and the optional ADI Dynamometer dynamic load to test Zing motor control performance with interface to MATLAB. The next steps would be to go to wiki.analog.com to learn more about the ADI high-performance servo drive and download the hardware design files and reference designs. Go to ez.analog.com to get answers for any questions that you might have related to the ADI high-performance servo drive hardware and reference designs. Visit the Avnet Intelligent Drives Kit webpage to learn more about the kit and purchase it. Visit matworks.com/zidk to learn about Matworks support for the Intelligent Drives Kit and for more information about the Matworks workflow for Xilinx Zing 7000 or programmable SoCs. Visit zboard.com to view the entire Zing motor control seminar. Thanks for watching.